Hello dear student, welcome to Time classes. In this session, we are going to discuss a very important concept from the chapter Mechanical Properties of Fluids, and the topic is terminal velocity. So first of all, I shall give you a brief idea about the concept of terminal velocity, and then we will discuss 2-3 questions from previous years for better understanding of the concept. So shall we start? So what is terminal velocity? Hope you are already familiar with the concept of viscosity and viscous force, right? So just consider a sphere which is moving through a viscous medium. Okay, so let it be a raindrop which is falling through air. Okay, so let us consider a raindrop which is having, say, radius r. Okay, and it is falling through a viscous medium, say air. Okay, and this viscous medium is having a coefficient of viscosity denoted by eta. So initially this raindrop will be in an accelerated motion due to gravity. But later what happens? Let's see what are the forces acting on this raindrop. Since it is falling through a viscous medium, of course there will be a viscous force exerted by the medium on the raindrop, right? So that will be definitely opposite to the direction of its fall. So the raindrop is falling downwards, so the viscous force will be acting in the upward direction. And also this is a object which is moving through a fluid, right? So definitely there will be a buoyant force as well, which is also an upward force. Okay, so buoyant force or upthrust. And there is also one more force which is nothing but the weight of this raindrop or gravitational force mg, which is acting vertically downwards. So these are the forces acting on this raindrop. Now when viscous force plus buoyant force becomes equal to the gravitational force, when buoyant force plus viscous force becomes equal to the gravitational force, the net force acting on this raindrop becomes 0, right? If the net force is 0, then acceleration would become 0. That means thereafter this raindrop will be falling with a constant velocity, and that constant velocity is called as terminal velocity. Okay, so hope now you are clear with the concept of terminal velocity. Now we have to obtain an expression to find the value of terminal velocity. Okay, so let's start from this equation. Buoyant force plus viscous force is equal to mg. Now we have to give substitutions for buoyant force, viscous force and this m. Okay, so what is the equation of buoyant force? Before writing the equation of buoyant force, let us consider the density of this raindrop as rho and the density of the medium through which it is falling, that is sigma. Okay, so here density of the sphere, it is rho, and the density of the medium is taken as sigma. Then how will you write the equation of buoyant force? We already know it is volume of the sphere into density of the medium into acceleration due to gravity, right? So volume of the raindrop into density of the medium. What is that? Here it is sigma into acceleration due to gravity. Now what is the expression of viscous force? Yes, according to Stokes law, we have an equation 6 pi eta r v, isn't it? Here eta is the coefficient of viscosity of the medium through which the sphere is falling, r is the radius of the sphere, and v is the velocity, constant velocity with which the sphere falls, and that is what you call as terminal velocity, right? So we can give it as vt. Okay, and that is equal to mg. Here I am going to give a substitution for this mass, that is mass of the sphere. We know density is equal to mass by volume, so mass is equal to density into volume, right? So what is the density of the sphere? It is rho, and volume of the sphere, it is 4 by 3 pi r cube. Okay, so rho into 4 by 3 pi r cube into g. So here also in place of volume of the sphere, you can give the same substitution 4 by 3 pi r cube. Okay, now just rearranging the equation, you will get 6 pi eta r into vt is equal to, yes, take 4 by 3 pi r cube common out, you will get rho minus sigma into g, isn't it? So from here you can obtain the equation of terminal velocity, that is Vt is equal to 4 by 3 pi r cube into rho minus sigma into g, the whole divided by 6 pi eta r, isn't it? So on solving this, you will get the final expression for terminal velocity as 2 by 9 r square g divided by eta into rho minus sigma, isn't it? So this is the equation of terminal velocity. You should by heart this equation for solving the problems related to terminal velocity. And the most important thing is that here you have to note the relation between terminal velocity and radius of the sphere. What is the relation? Terminal velocity is directly proportional to square of radius, isn't it? So we have to use this relation for solving certain type of questions. So I hope now you are well clear with the concept of terminal velocity. Now we are going to discuss 2-3 previous year questions. There we will see how to apply this concept for solving those questions. Okay. So let's see the first question. This is a numerical type question which came in one of the recent JEE Mains paper. So read the question. Small water droplets of radius 0.01 millimeter are formed in the upper atmosphere and falling with a terminal velocity of 10 meter per second. Due to condensation, if 8 such droplets are coalesced and formed a large drop, the new terminal velocity will be dash centimeter per second. So, before moving to the question, let me tell you something. In all kind of questions related to drop combination or drop splitting, you have to keep one point in mind. Let's see what is that point. See, let us consider there are n number of small identical droplets which coalesce or combine together to form a big drop. Okay. So let small r be the radius of the small drop. Okay. They are all identical droplets. So small r is the radius of each of the tiny drop. Okay. And capital R is the radius of the big drop formed. Okay. Now we have to obtain a relation between small r and capital R. See, it is well clear that the volume of the big drop formed will be equal to n times the volume of each of the small drop, right? Shall I write that equation? The volume of the big drop formed is nothing but 4 by 3 pi r cube. This will be equal to the volume of n number of tiny droplets. Okay, so we have n number of tiny droplets. So this is equal to n into volume of each of the tiny droplet, which is 4 by 3 pi into small r cube. Okay. So from here 4 by 3 pi gets cancelled and you will get r cube is equal to n into small r cube. Or you can write the equation as capital R is equal to n raised to 1 by 3 times small r. So this is a very important relation. Keep this relation in mind. You can use this relation for solving all kind of questions related to drop splitting or drop combination. Okay. Now come back to our question. Here the radius as well as terminal velocity of each of the small drop is given. Okay. And what you have to find is the terminal velocity of the big drop. So we already have the relation between terminal velocity and radius of the drop, isn't it? What is that relation? Terminal velocity is directly proportional to square of radius. So here let us take small letter v as the terminal velocity of each of the small drop and capital V as the terminal velocity of the big drop formed. Using this relation, capital R is equal to n raised to 1 by 3 times small r, we can obtain the relation between capital R and small r. Here what is the value of n? We have 8 droplets, isn't it? 8 small droplets. So value of n is 8. So capital R will be equal to 8 raised to 1 by 3 times small r. 8 raised to 1 by 3 is nothing but 2. So you will get capital R is equal to twice small r. That is, the radius of the big drop formed will be double the radius of each of the small drop. If radius is doubled, then according to this relation, the terminal velocity will be increased 4 times. isn't it? So the terminal velocity of the big drop will be equal to 4 times the terminal velocity of each of the small drop. So here what is the value of terminal velocity of each of the small drop? It is given in the question as 10 centimeter per second. So 4 into 10. The answer is 40 centimeter per second. No need of any unit conversions because in the question you are asked to find out the answer in centimeter per second itself. And also here you don't have to use this data regarding radius, isn't it? If you are doing in this way using this relation, there is no need of substitution of radius as well. Okay, so we can easily solve the question. Hope the solution is clear. Now let's see the next question. This is also a previous year question from the recent JEE mains paper. In an experiment to verify Stokes' law, a small spherical ball of radius r and density rho falls under gravity through a distance h in air before entering a tank of water. If the terminal velocity of the ball inside water is same as its velocity just before entering the water surface, then the value of h is proportional to dash. So here we need to obtain a relation between h and r. What is h? H is the height from which the ball is falling. Okay. And the ball is falling into water, and even after entering the water, its terminal velocity is same as the velocity just before entering the water surface. So here is the water. The ball is dropped from a height say h. Okay. So what will be the velocity of the ball when it is hitting the surface of water? Yes, of course it is square root of 2gh, isn't it? You are already familiar with this equation. It is the velocity of free fall, isn't it? Okay. Now it is given in the question that the ball continues to move with the same velocity even after getting inside water. Okay. The terminal velocity is same as the velocity root of 2gh. So now the solution is very simple. Root of 2gh will be equal to the terminal velocity of the ball inside the water. We already know what is the equation of terminal velocity. What is that? 2 by 9 r square g by eta into rho minus sigma. So nothing to do much. Here what we need is just the relation between h and r. Okay. So from this equation itself it is clear that root of h is proportional to r square, isn't it? So what is h? H will be proportional to square of r square, that is r raised to 4. So that is the answer, which is option B. Hope the solution is clear. Now let's discuss one more question, which is a previous year NEET question. Okay, read the question. A small sphere of radius r falls from rest in a viscous liquid. As a result, heat is produced due to viscous force. The rate of production of heat when the sphere attains its terminal velocity is proportional to dash. So here we need to obtain the relation between rate of production of heat and radius of the sphere. So what do you mean by rate of production of heat? Heat produced in a unit time. That is nothing but power, isn't it? So we can use the equation of power itself. Heat production rate. That is nothing but force into velocity, isn't it? We have the equation for power as force into velocity. What is F? F is nothing but viscous force, isn't it? And we know according to Stokes' theorem, the equation of viscous force is 6 pi eta r v, where v is the terminal velocity of the sphere and r is the radius of the sphere, into, yes, one more v is there. So you will get the equation as 6 pi eta r v square. Okay. Now there is nothing much to do. We can solve the question in less step. The 6 pi eta is a constant. So we can write this as directly proportional to r into v square. We already know the relation between terminal velocity and radius. What is that? Terminal velocity is directly proportional to square of radius. Okay. So in place of v, if you imagine r square, then you will get it like this, isn't it? So finally this would be proportional to r raised to 1 plus 4, that is r raised to 5. So the answer for this question is option C. So I hope the answer is clear to you, as well as the concept of terminal velocity. Hope you understood how to apply the concept of terminal velocity for solving the problems. Hope you have enjoyed this session. We'll see you again. Thank you.